Right, in this lecture we are going to start thinking about the shear stresses. Now you'll be pleased to hear that this is probably the last lecture where we're deriving equations, or at least the last one before we have a numerical example to look at. And I have to say, up until this point, if you've found this stuff relatively difficult to follow, that's fairly understandable. This is all going to become an awful lot clearer in the next video when we actually work on a numerical example. It all sort of slots into place when we actually see a numerical example. So stick with me until then. Before we get there, we just want to think about the shear stresses here for a second. So in the previous lecture, we were talking about the principal stresses, and they are the maximum and minimum values of the normal stress. And we saw how they relate, or we saw how we could derive equations that give us those principal stresses, and indeed the angles of the planes on which they act. We did derive equations for those. Now we're going to do a similar thing, but for the shear stresses. So what I want to do in this video is I want to derive expressions for the maximum positive and negative value of shear stress, and also the planes on which they act. Okay, so that's what the objective is here. So we're going to recall from before that we had transformation equation 2, and again that was the transformation equation for shear. That was this guy here. Now the first thing that I'm actually going to confirm here is that, I'm going to confirm one of the observations we made at the end of the last lecture, and that was that it appeared to us that the shear stress was 0 on the principal planes, and we're just going to go ahead and confirm that now as a sort of a preliminary task here before we move on to look at the maximum shear stresses. So how would I prove that? Well, if I set tau x1 y1, if I set that equal to 0, okay, let's see what happens. Well, I'm going to say 0 on the left is equal to all this stuff over here on the right, and we can straight away rearrange that. We can rearrange, and if we rearrange it, we could rearrange it into the following form. Tan of 2 theta is equal to 2 times the tau xy over sigma x minus sigma y. Now that will be familiar because the last time we saw that equation we had a little p in here, and that's the same equation that gives us the angles of the principal planes. And remember, we got to this equation by saying tau xy is equal to 0. So that's our confirmation of what we saw visually in the last lecture, where we observed that the shear stress had a magnitude of 0 on the principal planes. So that's a pretty important result for us to know. On those principal planes, the planes at which we experience the maximum and minimum normal stress, the shear stress is going to be 0. So it's a nice little result to sort of stick in our pocket. So we'll just say here, just to get a little bit of text down here, this is the same equation we saw when determining the principal planes. And so the conclusion for us is that the shear stress is 0 on principal planes. All right, so now we've got that little result nailed down, we're going to move on and start thinking about the maximum shear stress, right? So this is one of the last things. This and then the angles that these shear stresses act on are the last things that we want to kind of derive. Max shear stress. We're going to take the same strategy, exact same strategy that we had, or we used when we determined the principal stress. Remember, we have an equation. Which is this guy here, which just describes essentially a sinusoidal wave, right? And we want to find the maximum, the local maximum in that wave. And so if we differentiate that equation, we obviously get the slope. If we set the slope equal to 0, what we're actually doing is identifying the point where we have a local max or a local min. So we're going to do the exact same thing here. We're going to start by differentiating with respect to theta. So d theta of tau x1 y1. So that's going to equal the following. Okay, and we're just going to rearrange. Again, we're letting it equal to 0. So here I'm letting that whole expression equal to 0 because again we're after the point at which the tangent to the curve is horizontal. And so let's do some rearranging. Okay, so I've put in a little s here, a little subscript s here. This is just to indicate that these are the orientations of the planes with the maximum positive and negative shear stress. And so we're going to have all of the things that we observed previously when we were working out principal planes. We're going to observe the same things here. And I mean, the main headline here is that we again have two values. There's again two values for theta s, and again the logic that drove us to this conclusion we covered when we were looking at principal planes, so I'm kind of skipping a little bit here, but basically the same logic leads us to this conclusion that we have two angles for theta s that are 90 degrees apart. Now let's compare that, right? Now notice the subscript s in here. Let's compare compare that with our expression for the tan of 2 theta p for our principal planes that we saw in a previous lecture. So compare with the tan of 2 times theta p. Now we derived this guy in a previous lecture, right? So that's going to be 2 tau xy over sigma x minus sigma y. So comparing this guy, remember, note the theta p here, it's a different equation. Okay, compare that guy with that guy, right? And when you do that, you can see that the tan of 2 times theta s is actually equal to minus 1 over the tan of 2 theta p, right? So where am I going with this? What I'm ultimately trying to do here is I want to get a nice easy to use expression, a nice easy expression, i.e. a simple expression that relates theta s to theta p, because really what I'm trying to find out is like what is the relationship between the angles of the principal planes and then the angles of the planes on which the max positive and negative shear stress occur. So there is a very specific relationship, angular relationship between these two sets of planes, and I just want to confirm it here. So if that all sounds a bit cryptic, you'll kind of see, as I say, you'll see where I'm going with this now shortly. So let me just, so we know that tan is equal to sine over cosine, right? So I'll just say on the left I've got sine of 2 theta s over the cosine of 2 theta s, and that's equal to minus, we just invert it on the right hand side, so that's going to be the cosine of 2 theta p over the sine of 2 theta p. Now we brought this guy over to the other side of the equal sign, and in fact we didn't. That should in fact be plus, because now we've brought it over, and that means on the right hand side we have it equal to 0. So now I'm going to get this down onto one line. So I'm going to have sine of 2 theta s times the sine of 2 theta p plus the cosine of 2 theta p times the cosine of 2 theta s. All right, that expression there, I'll just say here, is equivalent. You want your table of trigonometric identities handy when you're doing these derivations, because we're relying on a lot of them. So that actually is equivalent to the following. It's equivalent to the cosine of 2 times theta s minus 2 times theta p, right? Just a standard trigonometric identity. It's equal to 0 still. The inverse cosine of the cosine of 2 times theta s minus 2 times theta p, right? Inverse cosine of all that is going to be, you got to do the same thing on the right hand side, so that's going to be cosine inverse of 0. Well, obviously that's going to cancel with that, and you're going to end up with 2 times theta s minus 2 times theta p. Inverse cosine of 0 is 90. All right, and we're starting to get closer now. Divide across by 2, and we'll say theta s minus theta p is equal to 45, and so here we go. Theta s is equal to theta p plus 45 degrees. Okay, we're nearly there, right? So what's that saying? That's saying there's a relationship here between theta s and theta p, and ultimately it's really saying that the angle of the planes in which the maximum positive and negative shear stress occur, they are orientated at 45 degrees to the principal planes. And so I'll just say here, remember that there's actually two values of theta s 90 degrees apart. So what we could actually say is theta s is equal to theta p plus or minus 45 degrees. That's where we were trying to drive to here. So we've worked out our angles, the angles of these planes. Now we can just add a little further note here just to say that, remember, there's two angles. So theta s1 is going to equal theta p1 minus 45 degrees, and that is going to be the plane of the maximum positive shear stress. And then theta s2 is equal to theta p2 plus 45 degrees. And that is going to be the plane of the maximum negative shear stress. If you are finding this complicated or you're starting to get lost, don't worry, because once we do an example of this, it's all very abstract here. Well, I personally find this very abstract to look at. But when we start looking at this with a numerical example, it's going to become even easier. And then we're going to move on to look at the Mohr circle interpretation of all of these equations, our representation of all of these equations. And that really collapses this down into a very straightforward problem or type of analysis. So hold out for more circle, because that's the ultimate trophy at the end of all this, because it allows us to do all of this stress analysis in a much more intuitive way. So we've got the planes of the maximum shear stress, and they're at 45 degrees to the principal planes. Right, let's just capture that in a quick note here. And again, we're going to go back to the same sort of strategy we used when we were working out our principal stresses, right? So remember, we said that if the tan of 2 theta s is equal to this, which we've seen above, well, if the tan of 2 theta s is that, well, then the cosine of 2 theta s, again, just think about this in the context of a triangle, right? So if that's my triangle, right, and that's my angle, 2 theta s, well, the tan is opposite over adjacent, so that's going to be a minus sigma x minus sigma y over the adjacent. That's going to be 2 tau xy. That would make the cosine, and let's call that h. That would make the cosine adjacent over hypotenuse, right? So that's going to be cosine of 2 theta s tau xy over h. Now I've gotten rid of the 2 here because I've essentially divided by 2. So I've taken that 2 from there, tau xy, and I've brought it over here, so I've just divided by 2. That's why there's no 2 appearing here. And then the sine of 2 theta s is equal to minus sigma x minus sigma y over 2h, where h is the hypotenuse. Now, of course, the hypotenuse h is the square root of these two sides squared. Right, so these are the other, once we've worked out this guy, right, once we've sort of work that guy out, well, then the rest of these guys all just kind of drop out of that, and it's all based on this right angle triangle here. Okay, now why did we do all that? We did all of that because we're going to take all of these expressions here and we're going to sub them into our transformation equation, right? So sub all of these into transformation equation 2, and remember that was tau x1 y1 equal to all that stuff. We won't write it out. And why are we doing that? We're doing that to get the maximum value of the shear stress. So again, it's just a little bit of algebra, so we've seen it once, so I'll kind of skip the steps, right? But basically, when you take those values and you sub them into our equation we had for tau x1 y1, what do you get? You get tau max. I'm defining it or calling it tau max now. Right, it's going to be the square root of sigma x minus sigma y over 2 to be squared plus tau xy to be squared, and that's no surprise, that's equal to h, right? So tau max happens to be the maximum value of the shear stress, happens to be h. Now another way to get tau max, right? We'll just work our way through this. Another way to get tau max is to do the following. Take sigma 1, our expression for sigma 1, we saw that previously, and subtract our expression from sigma 2 from it, right? So take sigma 1 minus sigma 2, what would you get? Well, remember, there's a long expression for each of those, and if you subtract them, you'd end up with sigma x plus sigma y over 2 plus h, all right, minus, so what is that? That's just sigma 1 minus sigma 2 was just sigma x plus sigma y over 2 minus h. So take all of that away from it. What's that? That's just sigma 2. Right, so when you do that, what do you end up with? You end up with sigma 1 minus sigma 2 is equal to 2h. And so h, which we know from here, happens to be equal to tau max, is equal to sigma 1 minus sigma 2 over 2. That's another very handy expression, right? Because what's that? That means once you've worked out your principal planes and you've worked out your principal stresses, your sigma 1 and your sigma 2, well, if you've got sigma 1 and sigma 2, you can plug it straight in here to work out the maximum shear stress. And if you know the angles of your principal planes, well, then you can just offset by 45 degrees, plus and minus, and you're going to get the angles that these maximum shear stresses occur on. So that's a really handy little result. So we'll just say this is the maximum positive shear stress, and then the maximum negative shear stress is just the negative of that value. All right, so we've all the derivations done. At this point, I want to jump back over into our Jupyter Notebook, and I want to calculate these values for this value for tau max. I want to plot it onto our graph, and I just want to see, or essentially confirm, the values in our graphs by plotting these values directly on. So let's pick that up over in the Jupyter Notebook. All right, so here we are back over where we left off previously. So what do I want to do? Let me just tidy this plot up first. So I'm going to get rid of these guidelines. All I'm going to do is comment them out. So I'll just command and slash, that'll get rid of those. And what else do I want to do? I want to comment out these statements. So these were the statements for our principal stresses and principal angles. Let's comment those guys out. Let's run that again. Okay, so let's get rid of these vertical guidelines as well. So we'll ditch those two. All right, excellent. So this is a raw plot of our transformation equations. And just for a reminder, remember it's the red one here that we're focusing in on now. So this is the variation of shear stress as the angle of the face changes, right? So this is what we're focusing on. So we've just derived equations that will identify the value, the magnitude or the value of the shear stress at this point here and at this point down here, okay? And we've also identified equations that will give us the angles of that point there and that point there. So let's just calculate those and then plot them onto the graph just to make sure that they land in the right place and it all makes sense. So the first thing I'm going to do is calculate the maximum shear stresses. So let me come in here, give myself a heading. Right, so let's just call this tau max positive. That's going to equal 0.5. Now see, this is where having the principal stresses already calculated is super helpful, because I can just use them straight away. So I can say 0.5 times sigma 1 minus sigma 2. Sigma 2, if I can remember how to type. Okay. Straight away, that's tau max. That is your maximum shear stress obtained because we already have the principal stresses. So I'm going to copy this down and say that, well, the negative version is just the negative of the positive version, tau max p. All right, and now we're going to plot our principal planes. It's going to be a very quick one, this. So not my principal planes, my planes of maximum shear stress. Planes of max shear stress. Right, let's call that theta S1, and that's going to be equal to, again, theta 1d, right, minus 45, and then we're going to have theta S2 is equal to theta 1d plus 45. Again, this is just coming straight out of our notes, what we've just derived. Right, now let's go and plot ourselves a few lines just to visualize those positions on our graph. So now what can I copy here? I'm going to copy all this, right? I'm going to come down here, I'm going to uncomment this. I'm going to change this from guidelines for max shear stress. Right, so what do I need? This is my horizontal line, right? So I'm going to plot tau max p, so these are the y coordinates, okay? So the x coordinates span from the left hand side of the plot, minus 180, over to the right hand side, plus 180. Let's plot these one at a time. So that means I want to get rid of those for now. Plot that. Excellent. So there's that cyan colored line, which is coming along, and it's just touching as a tangent off the very top of this sinusoid here. And so we've correctly identified the maximum value of the shear stress. Let's make sure that we get the corresponding angle correct. So now I want to uncomment this guy. I want theta 1s. Did we call it theta 1s? Theta s1. Theta s1 and theta s1. Excellent. Okay, so theta S1, I haven't actually printed out what the angle is, but when you plot it onto our graph, it gives us a vertical line landing in exactly the right place. So the combination of theta S1 and theta max gives us this point here, which is the maximum shear stress. Excellent. So it's confirmed everything that we've derived in our equations in our notebook, which is nice. So now let's just, for completeness, let's do the maximum negative tau max underscore n for negative, and we'll let that be lime. Yeah, okay, excellent. So we've got our negative, or our maximum negative shear stress, horizontal line in exactly the right place. And now let us just plot the vertical line, which gives us the angle. So that's going to be theta S2 and theta S2, again in red. Excellent. So here we have it here. So we've got this point down here and we've got this point up here. Both of those 2 points have been identified for us. Well, we've identified them for ourselves in our derivation. So the last thing that we're going to just observe before we wrap this up is to say that it looks like when we have our maximum positive and negative shear stress, if we trace those red lines, let's look at this guy in the center, this red line in the center. When we trace that red line, right, down, we can see, it is the case that the stress, the normal stress, sigma x, that is occurring on that plane, right, and the normal stress, sigma y, right, they are not zero. Okay, so the normal stresses that are occurring on the planes of maximum positive and negative shear stress are not zero. So we remember that when we were looking at the principal planes on which principal normal stresses act, it turned out that the shear stresses were zero on those planes, right? The reverse is not true. When you identify the planes of maximum positive and negative shear stress, they do have normal stresses as well, okay? And the last thing I want to do now before we wrap this up is just go ahead and work out what those values of stress are. So we'll jump back over to the notebook now for 2 minutes just to wrap up and work out what are the values of these normal stresses. All right, so finally, we're just going to make a quick note just to say that there are normal stresses that exist on planes of maximum and minimum shear stress. All right, so how can I come up with an expression for those, right? Well, it's going to be based on transformation equation 1, right? So what we're going to do is remember transformation equation 1. I won't write it all out again, right? But basically what we're going to do is we're going to sub in the cosine of 2 theta s, right? And remember we said that was equal to tau xy over h, and the sine of 2 theta s, and that was equal to minus sigma x minus sigma y over 2h. We're going to take that expression and that expression, which you'll recall we had here, okay? We worked them out here, or they dropped out of that expression actually. So we're going to take those two, we're going to sub them into our transformation equation 1, and that's going to give us the following expression. Again, I won't do the longhand simplification of it, but it's fairly rudimentary. You'd have no problem doing it. Sigma S1, let's just call it sigma S1, sigma theta S1 slash theta S2. That is signifying that these are the normal stresses that are occurring on this plane and this plane, right? Because it's the same stress, is equal to sigma x plus sigma y over 2. Simple as that, right? Simple as that. Whatever those planes, I'll just sketch it out here, right? But you can imagine that if I had an element at some orientation like this, and this happens to be the orientation that the maximum positive and negative shear stress occurred on, right? So let's just sketch something like that. Well then, the values of the normal stress, if I call that tau max, so we know they're all tau max, the values of the normal stresses that occur on those planes are going to be the same, the exact same stress on all 4 sides, and it's going to be, let's just call that sigma theta S1, and we'll call this sigma theta S2, and all that is, it's as simple as this, all that is the average value of the normal stress on two mutually perpendicular planes. Because remember, this top, doesn't matter what two perpendicular planes you have, because remember, the sum of the normal stresses on 2 mutually perpendicular planes is constant, right? So you could take any 2 mutually perpendicular planes. This top number here in the numerator doesn't change, it stays constant. So you just add the 2 together, divide it by 2, i.e. get the average, and that happens to be the value of the normal stress that occurs on the planes that also have the maximum positive and negative shear stresses. All right then, so that is about as much derivation as we want to do in this whole topic. What we're going to do in the next part of this discussion is we're going to take everything we've learned so far and we're going to actually apply it to a numerical example. And as I keep saying, as I've been saying all along, to try and keep you on board with what we're trying to do here, this is where it all really comes clear, and it's a lot simpler actually, really, when you actually see it put into practice with some numbers. And as I said previously as well, it gets even simpler still when we actually use Mohr circle to visualize all this, which is coming not the next part but the part after that. So take a break and we'll pick it up with a numerical example in the next video.